Every one of our technology platforms at our company, Reactive Surfaces, are based on utilizing the functionality in nature and in training that into a paint or coating system. And a coating is something that is applied at some point in the manufacturing process to protect something that's manufactured.
And here's what we're talking about. The natural carbon cycle puts a huge amount of carbon dioxide into the atmosphere every minute, but it also takes that down. It's a carbon cycle. But right now, human activity is putting into the atmosphere every single year anywhere from 30 to 50 gigatons of carbon dioxide. So it's the rate of photosynthesis, in other words, the rate at which carbon dioxide can be captured, times the amount of surface area that's photosynthetic. You mentioned leaves, stems, things like that are green. That surface area all combined times the photosynthetic rate gives you the amount of capture that's going to take place. So we need to watch how nature does it. We need to realize that nature does it using very thin layers, jam-packed full of photosynthetic microorganisms that are unicellular, spreads it all over the place on the land and on the water, and then lets photosynthesis occur. That's what we have to replicate.
Welcome to Mindful Businesses, presented by Sarani, and I'm your host, Beth McDaniel. In our podcast, we bring to you businesses that are mindful in their practices and processes. A mindful business employs sustainable social, economic, and environmental practices. Today, we have with us Beth McDaniel, President, and Dr. Steve McDaniel, CEO and Chief Innovation Officer of Reactive Surfaces, bringing surfaces to life. They join us from Austin, Texas. Welcome, Beth and Steve.
Thank you, Vidya. Thank you for having us.
Thanks very much.
We have in nature peats, bogs, wetlands, lichen that capture and sequester carbon. This is nature's way of cooling the planet. How exactly do peats and bogs and swamps do it? How do they capture and sequester carbon?
There's one mechanism by which carbon is captured by living portions of the nature, and that is through the photosynthesis. Photosynthesis is the capture of carbon and the combining up of carbon dioxide and water with the help of light from the sun to produce a carbohydrate, like a sugar, in particular glucose, plus oxygen. That's just the reaction that it is. There's all sorts of sophistication about that. We've tried for many years, humans have tried for many years to perfect that. And to date, that really hasn't been achieved. So the best example we have of photosynthesis is, in fact, as you say, in nature.
Nature doesn't, it sequesters CO2 sometimes, but then sometimes it releases. What we are here to do in the carbon removal world that we're going to talk about is to capture and sequester.
You explained photosynthesis, which is a basic science lesson for an elementary school or a middle schooler. And we were taught that chlorophyll, the color, the green, helps photosynthesis. Do the petals, the flowers, do they also photosynthesize?
Any green tissue, be it a stem, a leaf, or even a flower, portions of some flowers are green, is photosynthesizing. And that's because in those cells, they have a pigment called chlorophyll. And chlorophyll is very good at capturing photons of light from the sun and converting that into energy. And it transfers that energy to the photosynthetic reaction. So you talk about a bunch of green, what you're really talking about is a bunch of chlorophyll. And that happens in the ocean with algae. It happens anytime. It doesn't have to be a plant. It can be a bacterium. It can be a diatom, a small one-cellular eukaryotic organisms. It can be anything that's green.
Why is it that only green is able to take the sunlight?
That's a very good question. And the truth of the matter is it doesn't. You asked me about green a while ago, so that's what I talked about. There are other pigments that are light-capturing pigments. There are some reddish and orangish and yellowish, and those pigments you might find, interestingly, in organisms that environmental niches that don't have a lot of direct sunlight. So up in the Arctic, where the sun glances in at a very strong angle, a very narrow angle, you'll see a lot of reds and yellows that are photosynthesizing. That's because they have a different pigment. Yeah, there are other pigments besides green pigments. Vastly, however, photosynthesis is being done by chlorophyll or is being aided by chlorophyll pigmentation.
Explain the relationship between amino acids and photosynthesis.
The building block of peptides and proteins, amino acids, you can think of them as pearls on a string. There are about 20 some naturally occurring amino acids, and the sequence that they find themselves in puts them in close proximity to one another, like pearls on a string. There'll be some interactions between those amino acids. Maybe it might be something we call covalent, that is, they'll share a bond. Maybe it'll be something that's more like hydrophobic. In other words, two oily portions of them will come together, or two hydrophilic. In other words, two water-loving sections will come together. In a sense, then, what happens is that protein forms a three-dimensional structure. Peptides, on the other hand, are short strings of amino acids, not really pearls on a string per se, but short, maybe upwards of maybe 50 amino acids. Where enzymes, which are proteins, of course, can have thousands of amino acids in it. You'll hear some people say that peptides aren't active. That's incorrect. Peptides can have a lot of biological activity. Most of the hormones in your body are, in fact, peptides. Most of the enzymes, proteins in your body that do work, that will actually break down, say, a fat or grease and oil, or will build up a nucleic acid. Those are enzymes. And they have a very specific orientation in space. Many times they'll have at their heart a metal catalyst, zinc, copper, something like that. And they catalyze reactions. They are biological catalysts.
Fascinating. All this, I assume, are maybe the foundation to some of your inventions.
That's true. They're the foundation and the inspiration for all of our innovation. Every one of our technology platforms at our company, Reactive Surfaces, are based on, utilizing the functionality in nature and in training that into a paint or coating system. And so that's where the paint comes in. We are a paint innovation company, but we look to nature and we see a functionality. So Steve mentioned an enzyme that breaks down greases, fats, and natural oils. In nature, it does that. And so that's not our science, but what we do is harness that, and we want to put that into a coating system so that it will continue doing that enzymatic reaction, that functionality, but on a surface. And we can use surfaces then to create functionality. They become a canvas for functionality that we can paint on. When I use the words, by the way, paint and coating, those are used interchangeably a lot of times in the coating industry. But what a paint is a coating, has color in it. And a coating is something that is applied at some point in the manufacturing process to protect something that's manufactured. So if you look around you, everything that you see in your room, your furniture, your clothing, your shoes, your computer screen, glass that you're drinking out of, everything has been coated at some point. So that surface area in our world, that surface area that can be functionalized. And that's what we do, is we grab from nature, put it into a coating system. We know how to do that. We know how to stabilize things like enzymes and peptides, and in algae, in the case of carbon dioxide removal, in a coating system, and ask it what to do, what it does in nature, but then we control it in that coating system.
So let's pause for a minute and talk about carbon capture. Why is it so important to capture the carbon? Most of us have heard about global warming, climate change. We may believe in it, we may not believe in it. Give me some strong numbers and facts why I should believe that it is important to reduce temperatures by 2 degrees, to reduce the carbon in the atmosphere or other greenhouse gases.
That's a loaded question, and there are a lot of questions in what you just asked, okay? But certainly there are molecules, carbon dioxide is one, and there are other ones, methane and other ones, and chloro and fluorocarbons, that are very good at doing something, and that is they absorb heat. They absorb sunlight, and when they absorb that sunlight, they are capable of not only absorbing it, but re-emitting it. And if they re-emit it in a fashion that directs that heat towards the surface of the earth, then you will get warming of the earth, global warming. Not all molecules do that. Some actually do the opposite. Oxygen is pretty good at basically letting heat bounce off of it. Anyway, the oxygen, the molecules that we're talking about that are so pervasive in our environment is CO2. And you might say, and correctly you would say, Well, goodness gracious, CO2 is just naturally in the atmosphere. So what are you talking about? And here's what we're talking about. The natural carbon cycle puts a huge amount of carbon dioxide into the atmosphere every minute, but it also takes that down. It's a carbon cycle, and it's very balanced. There's an ocean carbon cycle. There's a land-based carbon cycle. Those are primarily mediated by small unicellular organisms, algae in particular, and blue-green bacteria. There's a lot of CO2 going to the atmosphere all the time, and you're like, okay, what's the big deal? Well, the big deal is this. That's a balanced system. When you add the burning and the combustion of hydrocarbons, in other words, oil, gas, things like that, releasing another huge source of CO2, then you are adding to the natural cycle. At some point, the natural cycle has to give up. It can't keep pulling down what we're putting into it. Not to scare you, okay? But right now, human activity is putting into the atmosphere every single year anywhere from 30 to 50 gigatons of carbon dioxide. Now,
that's 1 billion tons, by the way.
Yeah, and for your audience, just because I always have to remind myself as well, when we talk about what's the difference between 1,000 and 1,000,000 and 1,000,000,000. Well, 1,000 days ago, you were 3 years younger. 1,000,000 days ago, Jesus Christ hadn't been born. And 1,000,000,000 years ago, humans, as we know, Homo sapiens, the modern Homo sapiens, didn't exist. It was precursors to the modern Homo sapiens, and they were just learning how to bust rocks open and make tools. That's the difference between thousands and millions and billions. It's hard to actually get your mind around. But when we say gigatons, we are releasing anywhere from 30 to 50 billion tons per year of extra CO2, primarily from burning fossil fuels.
Wow. So you talked about algae, and I'm not sure if this is a relevant analogy. When you have an aquarium and you have algae, that is the system's way of creating something which will absorb the nitrogen?
You're basically asking a question we ask ourselves every day, is how is nature doing this? What are the tools? What math, what chemistry is happening for nature that we can emulate somehow? And really, it's pretty simple. In nature, you have a rate of photosynthesis. And as I told you earlier, we've been trying for years to make that go faster. No luck. Maybe a little bit, but not much. So it's the rate of photosynthesis, in other words, the rate at which carbon dioxide can be captured, times the amount of surface area that's photosynthetic. You mentioned leaves, stems, things like that are green. That surface area all combined times the photosynthetic rate gives you the amount of capture that's going to take place. Now, the truth is, the vast majority of that surface area is in the ocean. The vast, vast, vast majority of it. We all know that 75% of the surface of the planet is ocean. In those first layers of the ocean, we call that the photic zone, that photosynthesis is taking place. So it's a thin layer, jam-packed full of little bitty tiny microbes that are capable of photosynthesizing, and you just do the math. Photosynthetic rate times surface area.
But it's a very thin layer, and that's not enough to reverse the harm that's already done, to increase the amount of oxygen in the air.
It was for a while. Since the Industrial Revolution is when we started putting a whole lot of CO2 in the air. There for a while, in particular the ocean, is a pretty good sink for CO2. It will absorb it, producing carbonic acid. That's the same stuff that's the fizzy thing when you drink a cola, okay, the carbonic acid. Unfortunately, the absorption by the oceans of that carbonic acid have made the oceans much more acidic. And that acidic ocean is literally dissolving the reefs. They're made out of a material that is soluble in acid. And that's what's happening. The reefs are actually being eaten away at, taking away a home for many, many, many organisms that are dependent upon reefs. And reefs can be up way high up in the ocean. They can stick out. They can be next to the beach, or they can be even deeper. There are reefs that are down at hundreds and hundreds of feet of depth. But still in all, if there's so much carbonic acid there, so much absorbed CO2, it's going to dissolve it.
I had never heard about that effect of climate change directly from the acidity increase in the seawater, which were damaging the reefs.
What's scary, if you read about it, then none of the coral reefs in the world are expected to survive at this rate by the year 2100.
So within our kids' lifetime, possibly.
Yeah, all of the coral reefs will die if we don't do something.
So what do you propose, Dr. McDaniel? What is your simple and elegant solution?
When someone asks me, my son asks me, Dad, how do you paint a house? I'll say, well, go watch painters paint houses. If you say, I want to be a mechanic, well, go watch people fix cars. You have to watch the best examples of what it is you want to do. Well, the best example we have is nature itself. The nature is very, very good at it. So we need to watch how nature does it. We need to realize that nature does it using very thin layers, jam-packed full of photosynthetic microorganisms that are unicellular, spreads it all over the place on the land and on the water, and then lets photosynthesis occur. That's what we have to replicate. That's what we want to do, or at least that's what Beth and I learned when we looked at it carefully. And so that's what we're trying to do.
I mean, what else do you know that is spread out over vast amounts of surfaces in very thin layers and even has color? Paint. So we seem like we're in a business that we might be able to take advantage of some of this biomimicry.
What is that you're using? Are you using algae? Are you using lichen? Are you using plant material? What is your base material?
We're using algae. You got to keep in mind that that's what nature does. The vast majority of photosynthesis is taking place in algae. There are two types, well, there are all sorts of types of, but there are two main phyla, kingdoms. I'm trying to get my stuff down. But anyway, very large groups. There are eukaryotes, they have a nucleus, and there are prokaryotes. Those are bacteria, they have no nucleus. There are photosynthetic bacteria, and there are photosynthetic single cell algae. It's both of those groups. The photosynthetic bacteria, we call them blue-green algae, and other algae forms are like diatoms. Diatoms in the ocean are eukaryotic, single cell eukaryotic photosynthetic cells. We're using both. We have studies going on in our laboratories using actually both types of algae.
And do you grow these algae in your labs, in your facilities, or do you harvest it from nature?
Yes. Well, we're lucky to have connections into some of the premier algae manufacturing and genetic analyses labs. One of those is at Arizona State University, and the other one is at the University of Texas, premier in the world. Those are the best algologists you're going to find. So we count on them to give us different kinds of algae to test. But once they give it to us, they give it to us in small amounts. Then we can place it in the coating that we've built, the carbon capture coating, and it will amplify, grow and grow and grow and grow and grow. So all we have to do is transfer it from one sheet of material to the next sheet of material.
Almost like a culture.
Oh, it's a culture. Absolutely.
We start out with a small amount of algae, put it into the coating system, and then it grows within that coating system. And that's the art of our science, is allowing that to happen. It's similar to what you mentioned, Vidya, lichen in nature. Lichen are composed of two different organisms, a fungus and algae, the algae that we were just talking about. You look at lichen on a rock, we've all seen it, every color in the rainbow, and it's stuck to that rock. I mean, everyone at some point has tried to scrape off some lichen and said, how do you get this thing off? Well, it adheres well. Well, that's another quality of paint. Steve actually years ago was inspired by some lichen that he saw actually in a very remote Arctic scene. That's a lot like paint. And what the fungus does is it allows the algae to do what it does in nature, to photosynthesize, by providing it nutrients, allowing for gas exchange, allowing for the right amount of light to get into it, but not too much UV, and balancing it and allowing that algae to survive. And there are lichen that are like 1,000 years old.
Many thousands of years.
Yeah. And so they're very, very successful at doing so. So paint is kind of like the fungus part of that. And we put algae in it, and the paint is what we do. That's our day job. Okay. So we know how to make paint, how to engineer paint to do a lot of different things in our labs, to refract light or reflect light, or to keep UV out of it, or to allow more gas exchange, or to absorb moisture from the atmosphere. So that's how we can manipulate paint to allow the algae to photosynthesize as best as possible and do as much work as possible.
Can it over multiply? I'm comparing it to, say, a yogurt culture, which can get a bit too sour, not tasty for the palate. Similarly, if your algae culture overgrows, will that be a good thing or a bad thing?
Well, it turns out what we were glad to see this is that as opposed to algae just growing out in nature sort of without any restraints, which it can grow, algae blooms, in fact, can become a very big problem and kill fish and things like that in nature. However, if you train them into a coating, they'll only grow so much as that they can fill all of the empty spots in that coating, and then they'll just survive but not grow anymore. In fact, current studies in our laboratory are trying to figure out just how much growth can we expect, and it's quite a lot, into these coatings without them spilling out, and they just don't. It's a nature. It's interesting because you could ask the same question about lichen. Algae are in the middle of lichen. Why don't they spill outside of the fungus? That is what when we look at. And that's because, well, we don't honestly know, but we call it lichenized. Algae become lichenized. They realize they're in a constrained space, and they're only going to take up what space they have to so that they can survive.
Maybe it's nature's way of balancing, some sort of a symbiosis,
Yep, you're right. Lichen were basically the reason that we took this approach.
So you don't need to really stabilize it. It automatically gets stabilized. The compound or the mixture or the solution or the coating.
Automatic may be a stretch. We have paint chemists in our lab all over the place, and they spent a full year looking at every possible combination of paint polymer systems that could be even dreamt about working. And we finally came out with several, but it took a while.
Once you have started the process of growing the algae in your paint, is there at some stage that this can be altered due to exposure to air or oxygen or other elements? Does this compound need to be stabilized?
Yeah. And I think what you're asking is, okay, so you have a bunch of algae. What are you going to do with it? I mean, is it stable? Well, if you just put it out on the ground or you suck it in the ocean, the answer would be no. It would decompose and rot. So what we have to do is we have to harvest it from the coating. And one of the unique things about this coating is it's easy to harvest from. We harvest the algal cells, and then we subject the algal cells, which have all that carbon dioxide now concentrated inside of them. We subject it to a physical procedure called pyrolysis, and it is the burning of fuel like algal cells without any oxygen or very little oxygen. It's burnt with nitrogen. And what happens at the end of that process is you come out with something called biochar. It is vastly just pure carbon, 60 to 70, even more percent carbon. And all the carbon that you captured is now in this biochar. Now you say, well, great. So you got a whole bunch of biochar. Why are you excited about that? Because biochar is what we call durably sequestered. It's going to stay in that very same form for a very, very long time. In order to be called durably sequestered, it has to be not to have decomposed at all for over 100 years.
Can this biochar be used for creating other products, maybe throwing it back in the soil? One of our guests uses some carbon captured and from the air to make tiles. He uses it as a base raw material.
The biochar, in the case in what we're anticipating, is it can be used as a soil amendment because biochar naturally absorbs water from the atmosphere. And so it helps ground to become a better sink for carbon dioxide also. So it's cyclical in itself.
So now you have your paints, which are capturing the carbon, you have sequestered it. How and where do you apply this paint? Do you just have maybe grain silos, which are just painted with this, or cell phone towers, which are like omnipresent these days?
It's a great question. And that was the other part of the equation that we had to tackle. Okay, we have this paint, like you say. What are you going to do with it? Remember, it's surface area times the photosynthetic rate. And so that surface area is what we're talking about. Where is there that much surface area? It's true. Your surfaces in your house or outside your house and all these kinds of things are surfaces. But for the algae to grow, they have to be particular kinds of surfaces. We will be working on being able to expand the number of surfaces that they can be painted upon. But right now, we already have a pretty good solution. And that is we paint them on very large sheets of plastic that are a mesh, basically, which gives us a thin layer, but a whole lot of the coating on a very thin layer of plastic. And then we arrange these pieces of plastic in boxes, if you will. I'll talk to you about that in a minute. We call them modules, that we can get a lot of light into and a lot of these sheets into, and that we can stack vertically upon one upon the other. And so we can not take up a lot of ground space, but start taking up airspace.
Vertical space is something that paint can take advantage of. We've all seen paint on skyscrapers. It's lightweight, it adheres well, and we have an urgent situation on our hands. We need to pull down a lot of CO2. We don't have time to paint the north side of every building and hope that that does the trick. We want to maintain a good environment, the best environment for the healthiest environment for the algae to multiply. We want to contain them in modules with containing painted surface area as possible.
So are these modules portable in some ways?
Yeah, as a matter of fact, we could put all responsible in the United States. We're all responsible for about individually 16 tons of CO2 per year. Most people in the world are only responsible for about 4, but Americans are responsible for about 16. We could put just a few of these modules in your backyard, on your back porch, and it would balance out the amount of CO2 that you were responsible for. Or we can put them in larger organizations. We can put them right next to an industry where they're pumping out a lot of carbon, capture that carbon and do the same thing. Or we can put them in very large facilities where they're very tall, very high stacks, very spread out all over the place, and have thousands of them stacked as high as where you really want to go. Or we take them out of the module and just the sheets, and we lay them flat down on a marine surface, the ocean surface. And then you basically have as much area and surface area as you want.
So this brings to my next question about democratization of decarbonization, the environmental injustice, kids in areas where parents have to live close to industrial waste or industrial site. Would your solution help a situation in which a person or an individual doesn't have a choice but has to live in this area where the carbon put out in the air is far more than in an idyllic suburb, shall we say?
Well, I'll start by recognizing something you say, democratizing these kind of carbon reduction solutions. It's true, like the countries that have contributed the least to the problem are paying the biggest price. They might be in a place that's, in a warm area. They're going to be forced to move when temperatures go up and they can't stay where they are. We can expect to see migration and the likes of which we've never seen before, civil unrest as a result of it. But definitely we know that there are people that are paying a huge price that didn't even contribute to the problem. So that is one of the hugest injustices ever known. What we try to do is have as flexible of a functional carbon removal system that can be applied to various situations as possible. So like Steve was mentioning, we can put it up against we can actually capture the CO2 that's emitted from an industrial process, and that helps that industry mitigate or lower their carbon emissions. We are definitely working on an individual personal offset device, something that you could stack up, modularly in your backyard and take care of at least some of your carbon emissions, your carbon footprint, as well as being able to scale up to a gigaton level, and that's how we would do it in the ocean.
Here's the deal. There are many countries in the world in which when we talk about democratization, that suffer from the fact that they have lots and lots of people who are willing, women farmers, and primarily in Africa, that just need a crop. They need a way to grow something. If they can have 100 modules, and if they get paid $100 a ton for the amount of carbon they bring down, all of a sudden you make it so that micro farming becomes possible. You don't have to have a lot of water. You don't have to have a lot of nutrients. You don't have to anything but sunshine.
And they're the best suited to be able to do it would be farmers. Farmers
are going to have no problem with this technology. They're going to go, oh, yeah, I can do it.
They know how to make things grow, and that's what
they do.
This is similar to maybe getting carbon offsets to the Brazilian rainforest farmer. So there you're paying him or her to not cut down the trees. In contrast, here you're paying him or her to grow. And say me as a unconscious, not mindful consumer living in suburban America wants to buy carbon offsets. Is it possible that I use your solution as a way to buy carbon offsets?
Yes, as a matter of fact, for the last couple of years, we have been in the process of getting a certification from one of the carbon offset certifying agencies. The one that we've gone to is the gold standard, which is it's European based. It's one of the best. And so we wanted them to certify our technology to be able to sell it on the commodities market as a carbon offset. Where we are in that process is because this is a nascent technology, it's new it was invented by us. It has no methodology yet that and so there's nothing to rely upon certification wise. And so we had to take it through the methodology process, which is where we're at right now. It's probably a 12-month process, and we're somewhere in that 12 months. Once there's a methodology, then they can judge whether our system is doing what it should be doing. And anyone that comes after us that has a similar kind of system, they could judge theirs using this methodology as well.
Yeah, and
we just have to be the ones to develop it because we're the pioneers.
If I might add, we're making it seem a little simpler than it really is. In order to get the accreditation from the gold standard, say in Switzerland, you have to have done several things. Amongst them is you have to have submitted your technology, cradle to grave, to third party who undertakes what they call a life cycle analysis and a techno-economic analysis with the help of some of our colleagues at Colorado State University. And we have then submitted that paper to a peer-reviewed journal, the Journal of Carbon Dioxide Utilization. And I'm happy to say that it's about to be published, we believe.
Often our listeners want to know how much energy is your solution consuming? Is in the process of trying to do something good, are you doing more harm? How much energy does your solution take and how much is captured net?
So what we want to know, it's important to know that the process is not using more energy than you're actually capturing, because that would be not net negative. Every carbon removal system needs to be negative, meaning that you're capturing more than you're emitting in your process. And that is what the life cycle analysis that Steve was referring to does. It's a third party that comes in and analyzes all of your scope 1 and scope 2 emissions. Scope 1 emissions being the emissions that are inherent in your industrial process or in your process. And scope 2 are the emissions that take place because of whatever energy system you're putting into it. Like if you're taking it off the electrical grid, there's a formula for applying how much carbon accounting goes into your system. So the life cycle analysis does that balancing act to make sure that this is actually a net negative system. And ours was deemed net negative in that analysis. And the techno-economic analysis tells you what the cost per ton of that system in those boundaries that you've set up are. What it turned out for our system is that, because our system does rely on, it depends on what system you're talking about. The one that was outlined in our LCA was we weren't putting up very much energy in it. We weren't stacking the modules. We were just spreading them out and using solar energy. And there was a little extra energy that went into it. In that system, we had a 50% efficiency, which means that for every ton of carbon dioxide sequestered, we need to pull down 2 tons of CO2 from the ambient air.
It was 50 to 75%.
It was 50 to 75%. I'm very conservative when I say that.
No, you should be. And that's the way it is. There are other systems out there that their efficiency is quite low. There are other systems that is quite high. In those systems that is quite high, what you're going to find in general is that those systems are relying on free or waste energy, which is a very controversial term right now.
So I was introduced to you by a lovely gentleman called James Scott, who's the founder of the Embassy Row Project. It's a Envirotech pre-accelerator. I wanted to say thank you to James for introducing me to Reactive Surfaces and Beth and Steve. And this has truly been a fascinating conversation. But James Scott met you when you were one of the teams and the winners of the X Prize. The X Prize is a Musk Foundation endeavor which set aside $100 million to teams that had innovations to fight climate change. What was it to be part of this global competition?
It's very exciting. And yes, we're very appreciative of James Scott and the Virotech and all the work that he's doing to advance these groundbreaking technologies to help fight climate change. We did, before we met James, we did enter the X Prize Carbon Removal Prize. And just to be clear, we haven't won the prize. The prize won't be awarded until 2025. What you have to do in order to win this carbon removal prize, you have to actually build a facility that will pull down or capture 1,000 tons of CO2, capture and sequester that 1,000 tons of CO2 in order to win the prize. You have to do a couple other things too. You have to model your costs at a 1 million ton level. You have to show that it's possible to scale up to a gigaton level, because frankly, unless we can scale these technologies up to a gigaton, when you start playing with the math, you'll realize nothing really matters unless it can get up to a gigaton. Otherwise, we're not going to do anything about the problem. Even millions of tons aren't going to do anything about the problem we have. So we have to scale up to a gigaton. So we fully expect to be able to get to the 1,000 ton level, and especially utilizing some of the opportunities that are being presented by the Embassy Row project, which are opportunities in Eastern Europe that are very interested. For instance, Bulgaria, very interested in promoting some of these American technologies for solving climate change. And so we plan on building a pilot facility over there. The X Prize this is one specific X Prize. It is financed by it or sponsored by Elon Musk. Other X Prizes that are not sponsored by him, but this carbon removal one is. And so we'll know more on Earth Day 2025. So keep you posted.
There are several carbon capture and sequestering technologies out there. We've had a few on our show too. How is your solution better or comparable to your competitors?
You'll hear about some solutions that are technologies that absorb CO2 from the atmosphere and in sorbents or in solvents. There's some good technology out there. What you have to account for in a carbon removal system, though, is not just the capture, also the sequester, what you're going to do to permanently put it away. You'll hear about carbon capture and storage. And what that implies in the storage part of it is that the end of life for this CO2 in a lot of these technologies is to inject it very deep into the earth, like 1.5 miles or 2 miles down into the earth, into big saline formations or just these big formations where oil has already been pumped out of. And so they leave a big cave or, underneath the ground. And so they pump them into that and they just it's like, oh, okay, we're done with that. Well, but there's some questions about that. There are some definite risks of doing that. We think about, seismic activity. It's a lot like fracking is what it is. There's the seismic activity that could occur. There's leakage potential. There's possibility of contamination of water tables along the way that the CO2 could cause. There's all those things that in the carbon removal world, you'll hear about like carbon storage as foregone conclusion, and we don't really accept that. In order to do so, for instance, there would have to be tens of thousands of miles of pipeline built in order to get the CO2 where it needs to go to be injected down. As we mentioned before, use as the end of life for our CO2 in our system would be creating this biochar and then using that to spread onto farmland, for instance, to help the soils there. So we don't have to deal with that. And we think that's a big differentiator.
That's amazing. Thank you so much for sharing your wisdom, your invention with our listeners. And we can't wait to see it in everyday applications.
Yeah, if I had one final thing to say to you, Vidya, I would hope that the people who listen to you, at least your podcast, and I know there are quite a few, especially the young people, it can get pretty grim when you look at what we're being told. That is, that there really is not much hope about being able to pull down. That's not true. There's a lot of hope. We just need to have the willpower to do it, and we can do it. So the technology's there. Wires is amongst them. We can do it if we just focus on it and spend a little money to get it done.
And do it now.
Now.
We don't have 5 years to sit on this. We are passing at points of no return. So we really have to advance these technologies right away.
We say we don't want to build a world in which we can merely survive. We want to build a world which we can thrive in.
It's going to take some work.
Thank you again for coming on the show, Beth and Steve McDaniel of Reactive Surfaces.
Thank you, Vidya. Thanks to your audience for listening.
You're listening to Mindful Businesses, hosted and produced by Vidya Iyer. We'd love to hear from you. Send us an email at info@mindfulbusinessespodcast.com. If you learned a thing or two from this episode, share it with one friend. Click the subscribe button to be the first to learn about our latest episodes. We recorded this podcast in Buffalo, New York. Theme music was conducted by Tatum Gale. Roxanne Kurian is our marketing assistant. Our advisors are Anupama, Bushricha, and Jim Stone. This is Vidya Iyer with Mindful Businesses.